Now, I would like to start the second part of my lecture on the mathematical treatment of particle size distributions. Before the part 2 lecture, I will briefly review part 1. The content of part 1 is shown on this page. First, in part 1, I explained probability density, and probability density function for beginners of this kind of subject. After that, I explained number-based, mass-based, area-based probability density function. And I also explained things related to those functions. Finally, I explained specific surface and Zelter-Mean diameter D32. Part 2 begins with the cumulative size distribution. Then I will explain size distribution functions such as the normal distribution, log normal distribution, and Rosin-Rammler distribution and their probability papers. I explain various particle sizes such as D50, D84, D60, and D36.8. To understand the part 2, you should have the knowledge of exponential and logarithmic function to some extent. Concerning logarithm, the natural logarithm is used mainly in this lecture because it's convenient for expanding equations. If you feel that your knowledge about such subject is not enough, study it yourself. This page describes the measurement principle of cumulative distribution using sieves. In the measurement, sieves with different openings are replaced sequentially. The mesh opening size controls the flow of particles. That is, particles larger than mesh size remain on the sieve, and the particles smaller than mesh size pass through the mesh and fall downward. In general, quantities such as the number of mass of the particles measured. The sieve method is classified into the under-sieve method and the over-sieve method. The under-sieve method measures the amount of particles collected under the sieve. In this lecture, the symbol Fd is used to express the fraction of particles in the bottom container. The over-sieve method measures the amount of particles remaining on sieve. In this lecture, the symbol Rd is used to express the fraction of particles remaining on the sieve. Let's see the relationship between Fd and particle size d. Fd measured by the smallest mesh is plotted near the origin. When the slightly larger mesh is used, particle with d smaller than d2 accumulates in the bottom container under the sieve. The measurement result is plotted second. In the same way, the mesh size is increased one after another. Finally, all the particles are collected in the bottom container and Fd reaches the maximum value of 1. Drawing the line connecting the plotted point gives the red curve. particle diameter corresponding to f equals 0.5 is called the median diameter or median size. The symbol of median diameter is D50. The number 50 means 50%. Next, let's see the overshift distribution RD. The method is basically the same as the case of FD. When the smallest mesh is used, most particles remain on the mesh. When the sieve with slightly larger mesh is used, a little larger particles fall downward. The particles remaining on the sieve decrease a little. Similarly, the mesh size increases and R is measured. Connecting the plotted point gives the red curve. In the same way as the left figure, the median diameter D50 is found. The value of this median diameter is the same as the left median diameter. Usually, the median diameter is not equal to the mean diameter. At the bottom of this page, the undershift distribution F and the overshift distribution R are expressed by the probability density function F with D. You probably learned in high school math that the standard deviation sigma is used to describe the degree of data spread. The sigma squared is called the variance. The variance is defined on the first line. The symbol D with superscript number in parentheses is the size of an individual particle. The symbol large M is the number of all particles. In this lecture, N is used also for particle numbering. I suppose that the expression on the first line is familiar to everyone. But if the number of particles becomes huge, we have to resort to another formula using probability. In the pattern lecture, we have grouped the particles in the order of size before considering probabilities. Particles are grouped by the size, such as D1 group, D2 group, etc. The subscript symbol large M is the number of all groups. Usually, L is much smaller than M. In this lecture, L is also used for group numbering. There are 4 kinds of group data, such as number, length, area, and mass of particles. Corresponding to such grouping, there are 4 kinds of mean size too. That is, number-based mean size mu0, length-based mean size mu1, area-based mean size mu2, and mass-based mean size mu3. In this lecture, I omit the length-based mean size. The subtotals of group data are summed and divided by the total number N, or the total area S, or the total mass M, to obtain the variance as shown on the second to fourth line. The variance in integral form is shown by the first equation on the fifth line. The variances of the number-based, area-based, and mass-based are obtained by selecting the mean size mu and FD for each base. Taking apart the squared term in the integrand, you can see that the integrand is separated into three terms. The second and third integrals on the sixth line are the mean particle size mu and 1, respectively. Finally, the variance is expressed to be the mean of t squared minus mu squared. Later, I will explain that the equation on the seventh line will be used to calculate mean size mu and variance of particle size if the sides follow the log normal distribution. Please keep it in your mind. If all the particles have the same size, the standard deviation is 0. Such particles called monodispersed particles, but monodispersed particles do not exist in practice. In order to apply the concept of monodispersity to real particles, there is a criteria which is widely used in the field of engineering and technology. If the standard deviation is less than 10% of the mean particle size, the particle regarded as generally monodispersed in practice. Next, I'll explain the following three formulas of distribution function: the normal distribution, the log normal distribution, and the Rosin-Rammler distribution. The normal distribution is also called Gaussian distribution. Before explaining the normal distribution, I would like to speak about the exponential function y equal exponential minus x squared. The integration of this function from minus infinity to plus infinity is root pi. The error function is one of the special functions, and it's defined using the form of equation 2 as shown by equation 3. A numeric table like the trigonometric function table is available for the error function. Part 2 often expand equation with the help of the error function. That's why the error function is explained here. The normal distribution particle size makes use of the form of the above exponential function. Thus, replace y with the probability density function f, and replace x with particle size d. Since the normal distribution is a normalized function, the integral of ft over the entire domain is 1. Considering that normalization form, the normal distribution of particle size can be expressed by equation 4. The normal distribution has two parameters. The one is the mean size, mu, and the other is the standard deviation, sigma. The distribution f versus t is shown by the blue curve. The curve is symmetrical across t equal mu or across the mode diameter. When d equal mu, f takes the maximum value. Therefore, the mean size mu is equal to the mode diameter. The mean diameter, the mode diameter, and the median diameter coincide for the normal distribution. The number of particles whose site takes a value between x and x plus dx is given by equation 5. Using equation 5, the cumulative undersieved distribution can be expressed by equation 6. The expression of FD in the previous page is shown again on the first line. Without doing anything, it's difficult to get a concrete value of FD even if a value of D is specified. So on this page, I will show how to find a specific value of FD when a numerical value of D is given. Let's replace the index in exponential function with the symbol lambda shown in the second line. As a result, the integral over D changes into the integral over lambda as shown on the third line. Divide the integration range into two parts. That is, the part from lambda equals minus infinity to lambda equals 0, and the part from lambda equals 0 to a certain positive value of lambda. The first term of the first expression on the first line takes a value of 1/2. The formula shown on the fifth line is used for the above transformation. The second equation on the fourth line is slightly modified. Then FD can be expressed as shown on the sixth line. The second term in parentheses on the sixth line is the Euler function, which has been explained before. Values of the Euler function are provided in the numeric table as shown on the right of this page. Given the value of D, the value of lambda is determined from the equation on the second line. Then FD is determined from the Euler function table. In this page, I explain the site D84. The expression of the undersieved distribution FD shown on the previous page is changed from using lambda to using D, and it's shown on the first line. Let's see what value FD takes if D is equal to mu plus sigma. Substituting the equation on the second line into the equation on the first line, FD is equal to 0.841 as shown on the third line. The value of the Euler function, that is 0.6829, is taken from the table in the previous page. The diameter D given FD equal 0.841 is called D84. D84 satisfies the equation on the second line, so we can rewrite it as the first line using the relationship mu equal D50. Mu is replaced with D50. From the equation on the first line, you find that standard deviation sigma of the normal distribution is the difference between D84 and D50. Let me say about one comment. Particle size distribution is generally asymmetrical in powders and particles handled in the nature and industrial sites. Therefore, the normal distribution is seldom applied to particles in practice. Next, I will explain the low normal distribution. The left figure shows the frequency distribution F versus D of ordinary particles. In general, distribution F versus D is asymmetrical and has a long tail towards the right. Mean diameter mu, median diameter D50, and mode diameter D mod have different values. Change the scale of horizontal axis from D to log D. As shown on the right, the curve F versus log D tend to be symmetrical. That's because small scales in the D-axis are enlarged and large scales are contracted. Assign the variable x to log D. X is called log diameter in this lecture. If the curve F versus x can be regarded as a normal distribution, this distribution is called logarithmic normal distribution, or shortly log normal distribution. Many of the powders and particles we handle in practice have log normal distribution. From here on, I will develop various formulas under the assumption that the size distribution is log normal. The coordinates of log mu, log D50, and log D mod are indicated on the x-axis in the right figure. Due to the axial symmetry, log D50 is equal to the mean of log D and log mod diameter x mod. These three diameters lies on axial symmetry point. Here a new symbol mu0 is introduced for the mean of log D. That is, denote the mean of log diameter x at mu0. Next, let's express mu0 using a probability density function fx. Before that, consider a histogram for side distribution as we have done in part 1. Here, the case of number base is considered. The horizontal axis represents x and the vertical axis represents number. The width of the segment is delta x. The number of segment is L. Log diameters x1, x2, etc. represent a segment. Each segment has the number delta n1, delta n2, etc. as its data. The total of delta n1, delta n2, etc. is capital letter N. Using these assumptions, mu0 can be given by equation 1. I explained in part 1 that delta ni over large N is probability, and dividing delta ny over N by delta x gives probability density as shown in equation 2. Substituting equation 2 into equation 1 and taking the limit of probability density fxi, mu0 can be expressed by the probability density function fx as shown in equation 3. First, change the horizontal axis from x to x minus mu 0. The log normal distribution function is given by the equation on the first line. The range of d is from d equals 0 to d equals infinite, and the lower limit of d is 0. But the lower limit of log d is minus infinite. Therefore, the integration range of the normalization formula for the log normal distribution is changed from minus infinite to plus infinite, as shown by the second equation on the first line. Fx dx shown on the second line is the number of particles whose size takes a value between x and x plus dx. Using the equation on the second line, the cumulative anticipated distribution Ft can be expressed by the equation shown on the third line. Please note that lower limit of d is 0, but the lower limit of log d is minus infinite, as I mentioned above. In the description of the normal distribution, we modified it to obtain the numerical value of Fd. Exactly the same transformation can be done for the normal distribution. First, the index in the exponential function on the third line is replaced by the symbol lambda as shown on the fourth line. Rewriting Fd in terms of lambda, we end up with the equation on the fifth line. L for L lambda on the right-hand side is the Euler function. The Euler function is defined by the second equation on the fifth line. The values of the Euler function are provided in the numeric table. A part of the numeric table is shown on the right. Given the data of d, log diameter x is determined. Next, value of lambda is determined from the equation on the fourth line. Then Fd is determined from the Euler function table. The cumulative distribution is easy to measure, so it is demanded that logarithmic mean size mu 0 and logarithmic standard deviation sigma 0 are expressed by the cumulative distribution data. We have already seen that mu 0 equal log d50. In this page, I tried to derive the expression of sigma 0 as a function of cumulative distribution data such as d50 and d84. The derivation procedure is the same as in the case of normal distribution. First, the cumulative undersieve distribution Fd shown in the last part of the previous page is shown on the first line. Let's see what value Fd takes if x is equal to mu 0 plus sigma 0. Substituting the equation on the second line into the equation on the first line, Fd is equal to 0.841 as shown on the third line. The value of the Euler function, that is 0.6829, is taken from the table in the previous page. As I mentioned before, the diameter d given Fd equals 0.841 is called d84. X equal to log d84 satisfies the equation on the second line, so we can rewrite it as a fourth line. Using the relationship mu 0 equal log d50, mu 0 is replaced with log D50 from the equation on the first line. Sigma 0 is expressed by D84 and D50. The result obtained so far are summarized in this page. The figures show that cumulative distribution curve FD and RD for the normal distribution. D84 is the part side corresponding to F equal to 0.84. 0.84 of F corresponds to overshift distribution R equal to 1 minus 0.84, that is 0.16. As shown in the right figure, the part side corresponding to R equal to 0.16 is called D16. First, I'll show the case of the normal distribution. The mean side mu and standard deviation sigma are shown by equation 1. Next is the case of log normal distribution. The log mean side mu 0 and log standard deviation sigma 0 are shown by equation 2. The mean side mu n is given by equation 3. See Appendix 1 for the derivation of mu. The variance sigma squared is given by equation 4. See Appendix 2 for the derivation of the variance sigma squared. From the explanation so far, you realize that the mean diameter mu and mu 0, standard deviation sigma and sigma 0, median diameter D50, D84, D16 are key data. There are convenient papers by plotting measured value of the cumulative distribution on that paper. You can easily get the above quantities from the graph. The paper is called probability paper. The normal probability paper, the log normal probability paper, and Rosin-Rammler probability paper are examples of such papers. I explain the normal distribution, normal probability paper first. The first figure showed a graph of cumulative anticipated distribution F versus part side D. Both of the horizontal axis and the vertical axis are normal scales, and so the scales are evenly spaced. The blue curve is the measurement result. The normal probability paper is shown on the right. The scale of horizontal axis is the same as the left, but the scale of vertical axis is modified. The vertical axis is so modified that the normal distribution showed a straight line on the graph. Therefore, when the value of F is close to 0.5, scale spacing of the vertical axis is small, and when F moves away from 0.5, the scale spacing becomes larger. Since the normal distribution is mathematically defined by an exact formula, the vertical scale interval can be calculated theoretically, but such calculations are not necessary in general because normal distribution papers are commercially available or can be downloaded from the internet. I would like to say one thing about the difference in scale between the two. In the left graph, the minimum value of f is 0 and the maximum value is 1. However, in the right figure, the right graph, the lower bound of f endlessly approaches to 0 and does not reach 0. The same is true for the upper bound. So on the normal, on the normal probability paper, usually lower bound is marked like 0.001 or less, but not 0, and the upper bound is marked like 0.999 or more, but not 1. Here, 0.01 and 0.99 are used for simplicity instead of 0.001 and 0.999. As I mentioned just now, if the side distribution in the left graph is normal, it becomes a straight line on the right graph. The same normal probability paper as the above slide is shown below. Commercial normal probability papers have this shape. Many coordinate lines are drawn. As an example, measurement of the cumulative underside distribution F are plotted as white circles. You see that the plotted points do not form a straight line. So in this case, the distribution is not normal. Next, let's plot other measurement point with black circles. The black points show a straight line. Therefore, you can see the black point follow the normal distribution. Therefore, draw a straight line connecting the black point. This straight line represents a normal distribution. Once the straight line is obtained, D50 and D84 are obtained from the correspondence between the vertical axis and the horizontal axis. The mean size mu is equal to D50. The standard deviation sigma is obtained from the difference between D84 and D50. Next, the log normal probability paper is shown on the right. This probability paper is also commercially available and can be downloaded from the internet. The vertical axis for FD is the same as in the left figure. However, the horizontal axis is scaled logarithmically, so the scale interval is not even. As is indicated in the lower part of the figure, if we use common logarithm d or natural logarithm d for the horizontal axis, the scale interval will be even. Then that probability paper using the logarithm d as horizontal axis is the same as the normal probability papers on the left. The natural and common logarithm conversion formula is shown on the right of the log normal probability paper. The method of obtaining the mean size D50 and D84 from the log normal probability paper is the same as in the case of the normal distribution, that is, plot a cumulative amount, draw a straight line. D50 and D84 obtained from the correspondence between the vertical axis and the logarithmic scale of the horizontal axis. The log mean side mu 0 is given by log d50. The log standard deviation sigma 0 is obtained by the difference between log d84 and log d50 as shown under the graph. In order to get the mean size mu and standard deviation sigma, you must make calculation using the equation in the yellow frame shown on the right of the graph. Appendix 1, Appendix 2 should be referred for the derivation of these equations. The explanation so far is based on the undersieved distribution F. If the graph is based on the oversieved distribution R, you should find D16, which is defined in the oversieved distribution R. The treatment is basically the same as in the case of the undersieved distribution F. Microsoft Excel provides the soft lognormal.dis. Refer to it if you are interested. Finally, I will explain the Rosin-Rammler distribution. In general, the curve of the cumulative oversieved distribution R looks very much like the exponential function shown on the right. The left figure shows the relationship between y and x with various value of m. The curve narrows as n increases and widens as n decreases. In the Rosin-Rammler distribution, the cumulative oversieved distribution RD is given by the equation in the yellow frame. The symbols DE and N are parameters. As I just said, N indicates whether the distribution is broad or narrow. D is the particle size used to make the size D dimensionless. In the RD distribution, if D equals DE, then R equals 1 over A. Substituting the numerical value 2.71828 of E, R equals 0.368. E is called Napier number or Euler number. The letter E comes from the name of Euler. So it is found that DE, the particle size for which R is equal to 1 over E or 0.368. So DE is described as D36.8. First, I show the formula of the Rosin-Rammler distribution RD, which has been described in the previous page. This formula can be transformed to the second equation on the first line. Taking the logarithm of this expression, give the third expression on the first line. If you further take the logarithm of the third equation on the first line, you get the first equation on the second line. Transforming the right-hand side gives the second expression on the second line. If the left side of the equation is represented by y and the right side by x, we get the equation y equals nx. The equation y equal nx expresses the straight line passing through the origin with the gradient n. Next, prepare a piece of paper to write the measured value and relationship between y and x. If the value of logarithm is used for both vertical and horizontal axes, the scale can be a grid scale or normal scale, and the real number obtained by transformation from log to reals. When the coordinate axes are scaled logarithmically, the real number 1 over R and real number of particle size ratio d over dE can be read from the graph. Since it is easy to convert from logarithmic to real, I will continue to use natural logarithms in this lecture. Measurements of y and x are shown by red circles. Draw a straight line connecting the measurement. This straight line must pass through the origin. The gradient n is obtained from the slope of the line. If you want to find median diameter d50 from this graph, you should find y corresponding to R equals 0.5. Then y is found to be minus 0.3665. The median diameter d50 can be obtained by reading x corresponding to this y value and by converting it from logarithm to real number. Rosin-Rammler distribution is the particle size distribution formula developed by Rosin and Rammler in 1933 to express the cumulative distribution of parabolized curve. This distribution is suitable for particles with a wide distribution. The Rosin-Rammler distribution is also called the Weber distribution. Appendix 1 shows the derivation of the number-based mean size mu when particles follow the log normal distribution. The yellow frame on the first line shows the equation of the mean size expressed by the log normal distribution function. D is expressed by x, the right side of that equation. Substitute the log normal equation to fx. Rewriting d as exponential x gives the second expression on the second line. Putting the constant part out of integral and connecting the two exponential functions together gives us the equation on the third line. There are two terms containing x in the exponential function. If you combine these two x terms into one, you obtain the equation on the fourth line. As shown on the right side of this equation, let's put x minus mu 0 minus sigma 0 squared over sigma 0 as the new symbol t and replace x with t. Then, as shown on the fifth line, we can transform the integral over x to the integral over t. The constant part in the integrand on the first line is outside the integration. The part with red underline on the fifth line is the integration of the error function from minus infinity to plus infinity. The value of that definite integration is 1. the expression on the first line becomes the second expression on the fifth line. If you transform it further, it becomes the first expression on the sixth line. From the relationship shown below the sixth line, exponential mu0 is d50. So finally, we get the second expression on the sixth line. The second expression on the sixth line is shown again in the yellow frame. mu0 in this equation is determined from d84 and d50 as shown in previous pages. Appendix 2 shows the derivation of variance sigma squared given by d50 and d84 for the log normal distribution. It's shown on page 3 that the variance is expressed as the mean of d squared minus mu squared. The first equation on this page is that expression. If the particle size distribution follows the log normal distribution, fddd is replaced by fxdx. The integration range also changes. Substituting fx to the log normal and expanding equation finally lead to the formula of the variance, which is shown in the yellow frame. The expansion of the equation is similar to Appendix 1. I will omit verbal explanation of formula transformation here. The transformation procedure is indicated by the numbers from 1 to 6. So please check the transformation yourself. If you want to check it carefully, copy the screen by taking the screenshot and check the procedure at leisure. This concludes my lecture part 2. Thank you.